Let's look at another example, this time from methane, which is CH4. And again, the same kind of question. How do you go from carbon with 1s2, 2s2, 2p2 atomic electrons, how do you go from there into 109-degree angles as predicted by Vesper, i.e. the tetrahedral electron pair geometry? And like before, what Pauling said is that in valence bond theory, the central atom orbitals are hybridized, and at the same time then they end up being the same energy, so they all want to get as far apart from each other as they can. And if you have 4 electron clouds, they definitely want to be in tetrahedral arrangements.
The valence orbitals of carbon are the 2s orbital and the 3 2p orbitals. When these atoms form methane, their orbitals are thought to hybridize to form 4 equivalent orbitals. Because each hybrid orbital for the carbon atom is composed of 1 part s orbital and 3 parts p orbital, they are called sp3 orbitals. The energies of the hybrid orbitals are the average of the original atomic orbitals.
So I like this video a lot. It shows how you take the 2s orbital on carbon and the 3 2p orbitals on carbon, and you hybridize them. And again, hybridization just means you're mixing them. And I also like in this video how it showed how the 2s orbital went up in energy and the 3 2p orbitals came down in energy. And at the end, they were all the same energy level. All right. And this is important because in science, you're not supposed to create or destroy any energy. And you're just rearranging the energy to make them all the same value. And once they are all the same value, they want to be as far apart from each other as they can. That's where the tetrahedron arrangement comes from. So when you make a CH single bond, like in CH4, that single bond is a result of an sp3 hybridized orbital on carbon and a 1s orbital, atomic orbital, mind you, in hydrogen. And they form overlap, they form the sigma bond and stuff like that. So, like before, the electron pair geometry will tell you what the hybridization is. And if you see a tetrahedral electron pair geometry, you know that that atom has been sp3 hybridized. And sp3 comes from the fact that each of those 4 orbitals is 1 part s and 3 parts p. And again, I don't know why they made this stuff up, right? I'm just the messenger here. However, that's the origin of it, so now you know what's going on.
A methane molecule forms when 4 hydrogen atoms form sigma bonds to the sp3 hybrid orbitals of the carbon atom.
So in this video, they show those little teardrops, which is kind of like the mushrooms we saw earlier. All right, sometimes people use these teardrops, sometimes they use mushrooms, but those represent the hybridized orbitals. And carbon has 4 of them, 4 sp3 orbitals. So when you make a CH bond, the outer atom just has its regular atomic orbital, 1s in this case, since it's hydrogen. And that overlaps with the sp3, so you end up making the sigma single bond like that. Pretty cool. So again, the takeaways. The electron pair geometry will tell you what the hybridization is. Tetrahedral always means sp3. sp3 means tetrahedral. And when you make a bond, it's the middle atom which is hybridized. The outer atom just stays the same. It just uses its atomic orbitals. So there's no hybridization of hydrogen, for example. It's just the carbon which has been hybridized. And that's where tetrahedral comes from. This is another view just to make sure this is clear. So on the left-hand side, you see 2s and 2p orbitals in carbon. And initially, one of the 2p's is empty, but it's still there. You have 2 electrons in 2s and 2 electrons in 2p. And then they mix or hybridized into 4 equivalent sp3 hybrid orbitals. And you can see in the boxes on the right, all those little arrows are all at the same energy, 1 electron per orbital. So those represent the 4 sp3 orbitals. Now in the last video they showed kind of like a teardrop looking thing. Now they're back to the mushrooms. It depends on the authors and stuff. I think the mushroom is actually technically more correct, but at this level you wouldn't see anything. It's smaller than light. But anyway, I digress. So then in methane, CH4, it's the inner hybridized orbitals that bond with the atomic orbitals of the outer atoms, in this case hydrogen, to make the sigma bonds. So without hybridization, you wouldn't have molecules form, which is kind of a cool thing. This is a summary of the different types of hybridization that are possible. And I want you to look at these terms: sp, sp2, sp3, sp3d, and sp3d2. And these are going to be important. You can always find the hybridization from the electron pair geometry. So for example, if you see one of the examples from the last chapter that's trigonal bipyramid, you know that it's sp3d. And that means that to make one of those orbitals, it took one s, 3 p's, and 1 d orbital to make it happen. And that means because you put 5 orbitals in, you're going to get 5 orbitals out. 5 orbitals will get to the place of maximum distance between each other. Welcome to the trigonal bipyramid, etc., etc. So valence bond is pretty cool for normal kind of operations. You can figure out quickly how the things form and stuff like that. It doesn't have the rigor of molecular orbital theory that we'll talk about here pretty soon, but it is kind of interesting. And again, it works well when chemists are talking at a coffee shop, say, all right, because you don't need fancy computers. You can just kind of talk about things on the back of an envelope, as they say. So it's pretty cool. One more thing. When you make a covalent bond, in this case, you always have to have an unpaired electron on each atom. So like for CH4, you had an unpaired electron on carbon in an sp3 orbital, and the hydrogen had an unpaired electron. And those two electrons come together to make the bonding pairs, all right, that we talked about, or in the sigma bond, which is really cool. Also, if you look on the far right, it says remaining p orbitals. Those will be important to us here in a little bit, I promise, but I haven't talked about them yet. We saw boron and boron trifluoride had 1 p orbital. Notice that if you have a linear electron pair geometry, you have 2 remaining p orbitals. We'll talk about this here in a little bit. Okay, so here's a question you might see. It says, what's the hybrid orbital set used by the nitrogen atom in ammonia, NH3? And to answer this question, what you really should do is first draw a Lewis structure. We did this in the last chapter. You can go back and look. When you do this, nitrogen is in the middle of 3 hydrogens, and there's a lone pair on top of the nitrogen. And we talked about how if there's a lone pair and 3 bonding pairs, 4 pairs total, that's going to give it a tetrahedral electron pair geometry. It's going to be the trigonal pyramid molecular geometry. The angles will be about 109 degrees, etc., etc. However, for us, what's important is the electron pair geometry, because tetrahedral always means sp3. So ammonia, in the nitrogen in ammonia, will be sp3 hybridized. The outer hydrogens just use their atomic orbitals, but that nitrogen, sp3. This shows some different combinations of atoms in their hybridization. So the top one there is beryllium dichloride. Now beryllium, boron, aluminum, gallium, those kind of things, they can sometimes be under an octet. And beryllium can actually be really under an octet and be linear. So when beryllium dichloride is made, the beryllium is sp hybridized. And you can see there how the hybrid orbitals, those 2 little mushrooms, are kind of literally as far apart from each other as they can, which means 180 degrees. So when they bond with the chloride, then you have an sp or hybrid orbital bonding to one of the chlorines, in this case 3p orbitals, making that sigma bond. The next one down is boron trifluoride. The boron is sp2 hybridized to make the trigonal planar structure you see. And the last one there is methane, CH4. The carbon is tetrahedral hybrid, is tetrahedral electron pair geometry. That means that it's sp3 hybridized. And those 4 sp3 hybrid orbitals get as far apart from each other as they can. They bond with the 1s orbital on hydrogen to make the sigma bonds. Good to go. So this is the kind of question that you might see. I'd like you to try and predict the hybridization in each of the atoms that are pointed to in those little arrows. We'll start in the lower left, and we'll go clockwise to the yellow one in the lower right. So the first one there where it says start, you can see it's pointing at the nitrogen. And that nitrogen has 3 bonding pairs, 2 to hydrogen and 1 to the carbon, as well as a lone pair. So 4 clouds means it's going to be tetrahedral electron pair geometry. And like we've seen, tetrahedral is always sp3. So anything that's tetrahedral will be sp3. Going to the red one, it points to that carbon, and that carbon has 1, 2, 3, 4 bonding pairs around it, 2 to the hydrogens, 1 to the nitrogen, and 1 to the carbon. 4 bonding pairs means tetrahedral. Tetrahedral means sp3. Go to the green one now. That carbon in the middle has a double bond and 2 single bonds, a single to carbon, a single to oxygen, and a double bond to oxygen. Double bonds and triple bonds count as one big cloud. So that's 1 cloud to the double bond, 2 and 3 clouds to the single bonds. So 3 bonds around it, or 3 clouds, if you will, want to be as far apart from each other as they can. That's trigonal planar. Trigonal planar is sp2. So that's the one that's a little bit different. But then last of all, that oxygen has 2 lone pairs and 2 bonding pairs, 4 clouds total. It is, you guessed it, tetrahedral. A lot of tetrahedrals in this area, as you can probably see. Tetrahedral sp3. So it's not too bad once you see it. And again, you could also do trigonal bipyramid as sp3d, octahedral as sp3d2, and linear systems would be sp.